Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I would like to welcome Ricardo Restrepo. Is that how you pronounce your name?
Yeah.
Okay. He's from Georgia Tech. He works with Prasad, whom lots of you, practically all of you know. So he's Prasad's student. And he is also a fellowship candidate, which is wonderful. This is not part of his fellowship interview, but we've just asked him to give us a talk anyway, since I'd like everybody, not just the people who are talking to him during his interview, to learn about what he's been doing, which is reconstruction and clustering for a class of constraint satisfaction problems.
Okay, thanks for the invitation, and it's a pleasure to meet everybody here. Okay, what I'm going to talk about today will be about two specific properties regarding constraint satisfaction problems. Specifically, the properties about. Okay, I'm going to talk about reconstruction and clustering. Okay, I'll introduce this in a moment for certain class of constraint satisfaction problem. But maybe what I will focus the most will be on studying certain conditions that we have to impose over constraint satisfaction problem for actually reconstruction and clustering to have sense. And okay, I will specify this in more detail in a moment. So let me start just defining what is a constraint satisfaction problem. Okay, maybe all of you know, but okay, let me just set some notation here. Okay, so a Boolean function is going to be a function just from the space +1, -1 to the k to 0, 1, so that basically we are setting the variables inside the Boolean function to be plus or minus ones, and the output is going to be 0 meaning unsat, or 1 meaning sat. Okay, so with this notation we can construct like any logical combination of variables. For example, a disjunction in which, okay, this is going to be 1 if and only if at least one of the variables is one of the spins, we can say is set to 1, or a disjunction of positive or negative literals in which here we have negate some of the variables. That is the SI here. We have negate some of the variables. So if this Boolean function is going to be sat if at least one of the variables is set equal to xi. Okay, so xi is going to be -1 if you have a negation here. So with Boolean function like this is that you construct the k-sat setting, for example. Okay, just disjunction of positive and negative literals. Another example of a Boolean function, okay, is how you define two coloring on hypergraphs. Okay, you're gonna given an hyperage you want through UK, the two coloring is gonna be satisfied if and only if not all spins are the same. Okay, so just some examples of Boolean function here that we can use in a great variety of settings. So a CSP is basically a set of Boolean functions plus a collection of variables put in certain way. So basically we have a set of variables, okay, size n variables. We have certain pool of clauses, I mean certain set of Boolean functions, and we combine these two in certain ways. So here we're assuming arity k for every one of the Boolean functions. So an assignment over the n variables is going to be a satisfying assignment for this CSP if and only if when you replace the variable by the spin assigned by the assignment, then you have satisfaction in every one of the Boolean functions. So given a CSP, we'll have certain set of satisfying assignments that is going to be a subset of all the assignments, and maybe you want to study that set. That's basically the goal of the theory of CSPs. But we want to introduce a level of randomness, just to allow us to construct certain class of CSPs. Basically, now we have the same set of variables. We have a pool of clauses, and we construct certain random CSP according to the following. We just choose the Boolean functions here to be independent elements from the pool of clauses, from the pool of Boolean functions, according to a fixed distribution P sigma, so that if we have in the pool of clauses, for example, a disjunction and a two-coloring clause, we can assign 1/3 to the disjunction, 2/3 to the two-coloring clause, and here we just choose with probability 1/3 the disjunction, with probability 2/3 the two-coloring clause. And the variables inside are going to be taken independently, uniform and random from the elements from n. Okay, so these are going to be independent. The indexes of the variables are going to be just independent, uniform, and random from 1 through n. So in principle, we can have the same variable in the same clause, for example. So the common setting we use for this kind of random CSP is going to be when the ratio of number of clauses or number of Boolean functions evaluated at variables remain two variables remains constant. Okay, so m is the number of clauses, like m is this number of Boolean functions evaluated at variables. N is the number of variables. We want that ratio to be constant. Why? Because at this scale is that interesting things happens. And the notation used for this kind of CSP is just CSP n, number of variables, alpha, ratio, and p sigma, that is going to be the distribution of over the pool of clauses. Okay, so everything will depend on basically on this and this, alpha and the distribution, and we want results when n is large. So some example of interesting questions we want to know about the space of satisfying assignment that now will be random because the CSP is random by itself. Okay, are the common questions like verifying if certain sigma is a satisfying assignment? Okay, that's not difficult. Or extending a partial assignment, or finding in reasonable running time a satisfying assignment, at least one. Or maybe something more difficult, sampling a satisfying assignment uniformly over the space of satisfying assignment. Moreover, we can just try to count the number of satisfying assignments to do this, translating to do an estimate of the partition function of the Gibbs measure associated, or maybe something more delicate, like counting or sampling satisfying assignments with certain discrepancy. The discrepancy is going to be basically the difference between numbers of ones in the satisfying assignment and numbers of minus ones. Properly scales, or maybe something more relevant or more complicated will be to deal with or to study the correlation between the variables when we sample from uniformly from the space of satisfying assignment, like long range correlation or the problem of reconstruction. So I'm gonna talk about this now, like, to define what we mean by reconstruction. So to define this, we have to first take in account that given a CSP, there is an hypergraph associated with the CSP. Like, we ignore the Boolean functions and regard the variables inside as edges of an hypergraph. Here is just a graph. Okay, I just put an additive to CSP. So the graph associated with this CSP is going to be this one. So that here we have a natural distance, the distance over the graph. So given a CSP, we have a natural distance between variables. That is the distance the distance induced by the hypergraph associated to it. So we want to study basically this long-range correlation, but the range will be respect to this distance, respect to this induced distance. So that let's sigma will be a uniform, a random satisfying assignment, choosing a uniform.
Slow down a little.
Okay.
So if I have a clause between k variables, then I put a k hyper edge between these k variables. So this defines a graph over the variables. Or if you want a graph on 1 up to a hypergraph on 1 up to n.
Yes.
And then the distance is just the graph distance in this graph?
Yes. So basically, your question is if you have,
so
for example, k.
between 7 and 4 is infinity?
Yep, that's right.
So if these were like random sat, you could think of a random sat falls into this picture, right?
Yes,
so you
that's
have
right.
Random sat, and then you would say the distance in two variables is the number of clauses you have to go through going from one variable to another.
Yes.
Adjacent clause.
Yes, that's right.
Going through the existing clauses of that random
It's in
sat
the same
formula.
clause,
So
these distances
right.
zero
So if two variables are in the same clause and their distance is 0
0 or 1?
Yes.
or 1
Okay.
or whatever,
Yeah.
and if they're not, then how
If they're
many
the
of
neighbor,
those
it's like an
steps do
example.
you
Yeah,
have
that's
to
right.
take?
And the problem about connectivity, okay, is not a problem because basically once you fix the CSP, the space, okay, and you take a random assignment from the space of satisfying assignment, okay, it's going to be independent between different connected components. Okay, so the spins, yeah, the spins are going to be independent. So
one variable in one
Decided
cluster
on it.
will
Decided on each
constrain
component.
the
Exactly.
variable in the other.
yes, if you are able to sample satisfying assignments here and here, then you are able to sample in the whole space, use the product measure. Okay, so this long,
The I there, is that D sub G should be 1 comma J maybe?
Oh, yes.
You're fixing one X1.
yes, there is a typo here. Yes, I didn't realize. Okay, so we have a fixed CSP. We choose a new uniform random satisfying assignment from the space of satisfying assignments, and okay, we have a fixed variable x1. So this should be x1, and this is just the set of all variables such that the distance is to this variable to x1 is greater or equal than r. So this should be xj. Yeah. In the induced distance with the distance in the induced hypergraph. So there are two kinds of long-term correlations that can be defined. One is called the uniqueness condition because corresponds to existence of a unique Gibbs measure. And it's the following. Okay, so the uniqueness condition is not going to hold if there is some assignment of the faraway variables, some assignment for the faraway variables, such that they are going to bias the spin at x1 to be okay, not to be equal to. Sorry, once again, here there should be a type. There is a type of 2. This is equal to 1. So first and all, here we can assume that the marginal at one variable, because let's assume that it's going to be 1/2, 1/2. So our CSP is that nice that the marginal of a spin at one variable is going to be 1/2, 1/2. Okay. But that is not a problem here. So the uniqueness condition doesn't hold if there is some assignment of the faraway variables such that now the spin at the variable x1, okay, the marginal to be equal to 1 is going to be far away from the unrestricted. Okay, given this assignment is going to be far away from the unrestricted probability. So basically this assignment is going to bias this to be far away from the probability we expect to be.
So now I have a question. The probability is with respect to the assignments of the variables or with respect to the randomness you have chosen
From
for
the
your...
from the assignment. Yes, with respect to the
It's
assignment.
all a fixed
Yes.
SAT formula.
So here we have
I
a...
don't understand how can you do the limit n goes to infinity because you choose, I mean you have chosen uniformly at random from... I mean,
Okay, so here there is a delicate thing. So basically, for every n, we choose gn to be a random. Okay, we choose a random CSP with n variables. But before than that, we fix like for every n, we fix a distinguished variable. This variable is going to be nice. For example, if for every n we choose x1 to be just a variable chosen at random. So basically, yes, in order to define launch range correlations, when n grows, we have to define basically a random CSP for every n and a distinguished vertex in every random CSP. That distinguished vertex is x1.
I see. So you independently for each n choose a uniform random CSP.
Exactly.
Okay.
A uniform random CSP and a distinguished vertex. That distinguished vertex can be good or bad. For example, we can in every step we can take that distinguished vertex to be in a disconnected component. So that is not gonna be good. For example, it's not interesting to study. But
when you now say the limit r goes to infinity, the quantity in the limit is actually a random variable with respect to some sigma algebra over the set of all satisfying, I mean all k-set problems over all n.
Yes.
So is this limit going to 0 in probability with probability
we want it to go in probability. Yes.
In probability.
Yes. So basically, this is gonna be this. Okay. Basically, here I have to be careful with two things. First of all, okay, that at every step there is going to be a distinguished vertex that will be the one that represents the variable x1. Second, okay, this is going to be lim sub 2. Okay, but anyway, this is increasing, and this is a random quantity anyway, and we want improbability to go to 0 for uniqueness to hold. So uniqueness is not going to hold if with positive probability this quantity. If with positive probability there is some assignment for the faraway variables that is going to bias the spin at x1 far away from 0 for certain subsequence over the n's and r's. Okay. So
the random CSP that you're choosing is a different one for every n.
yes.
Yeah.
Yes. Yes.
I mean, it's uniformly random.
Yes, that's right. Okay.
Why is this called uniqueness?
Okay, because it's called uniqueness because suppose at every step, suppose the induced graph at every step is going to be a tree. A tree. Okay, so we have another different kind of random CSP, but at every step is going to be a tree. And this tree somehow is monotone, so we can couple the trees in such a way that the edges are increasing, containing one in the others. So the Git measure that is induced by the spin by the satisfying assignments at every level is going to be unique. That depends on the yes, we can have several Git measures, or maybe one, maybe external measures, but here is going to be just one measure. Okay, maybe I'll explain this later.
A simpler example would be an easing magnet. This is a more complicated one, but an easing magnet, a faraway variable can't have any effect on the origin if you're at high temperature and there's only one state, this high temperature disordered state. When you're at a low temperature, if you put minuses on the boundary, it'll be biased to minus. If you put pluses on the boundary, it'll be biased to plus. The minus and the plus are two different gift states.
And it has no effect, absolutely no effect?
In the high temperature phase of an easy magnet, it has no effect because there's only one state. So whatever you do, that's the
So
state
if the
you're going to
boundary
get.
goes to infinity, I mean, if the bound, right, so you put conditions far away, they might influence you not in the limit as far away it goes to infinity.
I mean, I'm not sure exactly what it means. So this,
Okay,
just
I
to,
guess
just
that
to see if I
doesn't help.
understand roughly,
Yeah.
like what you're
And then
saying
you
is
have
that
uniqueness above and below. When high temperature and low temperature, you get uniqueness in both cases.
No, you only have the uniqueness in the high temperature.
so
And in a low temperature phase, it's non-unique, and you test that by trying to put something far away and seeing if it has an effect. If there's some long-range order, it has an effect. The unique phase is a phase without any long-range order. And that's what he's saying, basically. There's no long-range order. The boundary can't affect things. That's what happens in the unique phase. There's no long-range order. You only get one state out.
you're speaking physics.
Well, I mean, I'm speaking measure theory too, but yeah. Okay.
So basically, we can say the following: like vertices.
It helped her.
It's clear now.
So let me see if I understand. So you're saying, first of all, this definition says for any, there's no constant r such that you can set r faraway bits.
Yes.
Or it says, yeah, set all of the r faraway bits and influence at all
Yes.
this one particular bit.
Exactly.
The probability.
Exactly.
And what's unique is actually sort of the distribution over satisfying assignment.
Yes, but
it's
the
not
thing-
actually a particular
Yes.
assignment. Or is it a particular assignment?
Yes, but anyway, the name is just borrowed from the context of Git measure. That the problem is that here is not easy to define the limit in Gibbs measure because we have this sequence of random graphs, so that maybe of random CSP that may be such that the induced graph in every step has different geometrical properties. So we have to define some delicate embeddings in order to define a limiting Gibbs measure. But the notation is just borrowed from that because uniqueness, when you define properly Gibbs measure, okay, means that this condition basically implies that there is going to be a unique limiting measure, a unique Gibbs measure that has the marginals we require. Okay, maybe I'll go back to this at the end.
How you set your variables, your xi's, you're going to get the same measure out when there's a unique measure, because there's only one measure.
Well, let me formulate it differently. You could look at the set of measures obtained as follows. You have just the measures on this one variable, x1, which is sort of either plus or minus 1, right? Which is just, if you looked at all satisfying assignments, well, maybe x1 is half of the time plus, half of the time minus, maybe it's 1/3, 2/3, okay? And as you have larger and larger system, maybe it's always 1/2, okay? But now you could say, what if I look at all satisfying assignments such that xn is equal to plus, okay? Maybe actually once you make xn equals plus, you have so much correlation because you have a coloring problem, you sort of say, I color this vertex far away red, this forces my vertex x1 to also be red, no matter how far this other one is. So instead of starting with the set of all satisfying, all assignments which satisfy a formula, you look at those such that this far away variable is set to red. So maybe that introduces a new measure, or maybe that measure as the limit of n going to infinity and far away going to infinity goes away, the influence is lost. If it's lost, well then there's no way to get a different one, so that equals uniqueness.
And if there was long-range order, you could set it blue out there and get a different measure. You could set it green out there and get a different measure.
You can set all of them.
Except for those in your ball of
a
radius.
satisfying assignment, you could say all things which are far away are unsatisfied, are zero. All the bits which are far away are all zero.
Right.
You'd think that would increase the chance of this
Right.
bit being one, but that's not the case.
But that's not the case in the unique phase.
Sorry.
Yeah, so
It's a subtle, I mean, it's a subtle concept.
yeah, so I actually forgot. I had the picture here. Okay, maybe this can help a little bit. So we have here okay, use a distinguished vertex. I fix this to be in my neighborhood. Maybe I didn't count correctly the distances, but that's not the problem. And okay, for example, this assignment of these faraway vertices, will surely induce the color of this. Okay, we can here I use, for example, I use these edges that have the perpendicular line. I define them to be okay, that the Boolean function in there will allow only different colors, and the Boolean function for this will allow the same color, for example. So this particular assignment will fix this. And actually here it happens that any assignment that you put on this, that you put on this will induce the color of this, will bias the color of this. So there is no uniqueness. Basically, when you have uniqueness, if you are able to properly define the marginals, okay, there's going to be only one measure that has those marginals, because in principle you can have many measures that have certain marginals. So that's basically uniqueness. But the problem here is that okay, but the problem here with uniqueness is that you cannot guarantee monotonicity with respect to the ratio of closest variables. The uniqueness here is going to be is not that interesting. Like, doesn't depend too much on the spin system, but depends at principle in the geometry of the induced hypergraph. I'll say why in later on. So that a more interesting long range correlation definition is called the reconstruction problem. Basically here you don't require that there is some assignment of the faraway variables that will bias the distinguished variable, but basically what you require is that in average if in average you are able to bias the distinguished variable x1, okay, n and r going to infinity, then you say that the reconstruction problem is solvable. Otherwise, you say that the reconstruction problem is not solvable, and there are no long range correlations in this sense.
The average is over your Gibbs measure induced by the satisfying problem.
Yeah, that's right. And once again, this is going to be, the whole thing is going to be a random quantity. So you want this improbability to go to 0.
And the reason it's called a reconstruction problem also is that, like in phylogeny and other things like that, you look at the leaves and you ask, from the leaves, can I reconstruct what happened at the root? And if there's long range order, you can, with some reasonable probability, reconstruct what happened at the root. And if there's no long range order, it's unsolvable. You can't reconstruct it and figure out what's going on.
You're just introducing new words which we're not explaining. Don't use.
Well, but I mean, why is it it's reconstruction of what? So people like Elchanan and those work a lot on this, and Sebastian, who was here as a postdoc.
I just say remove the word long range order.
Oh, okay. Remove the word long range.
So when
otherwise you have to define that.
Okay.
So now
yeah,
when
it's a definition.
yeah, that's right. And now when you have non-reconstruction, you don't have necessarily uniqueness. But the thing is that if you are able to define properly a broadcasting, okay, the broadcasting distribution of the spins of satisfying assignment, then that's going to be extreme. That another borrowed term from the Gibbs measure notation. Okay. So the other interesting property to study here over the space of satisfying assignment is clustering. It's called clustering. This is more geometric than a probabilistic property. Basically, here you fix a threshold D max, but then you want that threshold to go to infinity with the n, but maybe at a slow rate. So a D max cluster of solutions is just a set of solutions such that you can go from one solution to the other. By solution, I mean satisfying assignment. So you can go from one satisfying assignment to other through satisfying assignments in steps of Hamming distance at most D max. So, okay, you can just swap some bits and obtain another satisfying assignment and go on. Okay, so the maximal set you obtain in this way, okay, that is called a cluster.
Do a perturbation of one satisfying
Yes.
assignment to another, or perturbation where the range of your perturbation is at most D
Yes.
max, then
Well, just flipping
Then it's a
Dmax.
cluster,
So it
right.
just means that by flipping Dmax bits one at a time,
right,
you can walk through your set of solutions.
right, or
Yes.
not.
Yes, that's right.
Well,
Clusters,
the
whatever.
cluster is one where you can't. Right.
So the set of solutions is going to be clustered. If when you look at the clusters, okay, maybe there's one cluster, maybe there are 2, 3, but the set of solutions is going to be complicated. That is clustered if it's partitioned into exponentially many clusters, and also even with this math, you allow these Dmax to go to infinity, maybe at a very low rate. Okay. So.
So if you needed, so if it's class, for example, assume choose Dmax equals 1.
Yes.
Okay? It could be that with Dmax equals 1, you have exponentially many clusters.
Yes.
But with any Dmax which goes to infinity, you don't, and then you call it not clustered.
Yes, that's right.
Okay.
Yes. So basically, because we don't know how small or how big should be this perturbation, like how to define a local perturbation. That should be a constant, but we don't know how big. So we have to put d mass going to infinity. Maybe at a low rate, but okay. So now I'll introduce some bunch of definitions over the Boolean functions that we need. Yep.
The goal of all these definitions is so we get like an you have some intuitions about the landscape of solutions to a random, random SAT or random CSP problem, and you're trying to get some intuition about those, and you use these definitions as a way to formalize.
Yes, that's right. And I should say the goal of this moment. Basically, the goal is going to be for certain class of CSPs that satisfy certain conditions. Okay, we are going to state what is going to be the location of alpha, where reconstruction or clustering or just satisfiability is going to be. That's the goal, and we will see which requirements we need. Yes, exactly.
The physicists have sort of for years been claiming that, okay, we understand why satisfiability is hard in average. And the reason is that there's this, so they didn't define any of these words, but they said the reason is because there are exponentially many clusters, you should think of them as exponentially many minimas in some landscape, and we can't go between these clusters. And the computer scientists have been saying to the physicists, you just don't know what you're talking about, you can't even define what it means. So now the community has gone to start to define what the physicists mean and try to prove at least some of the statements with the physicists always sort of just write theorem and they have not defined what it means, and they certainly don't have it.
But people like Bart Selman who do WalkSat and GSat and all of these, so these AI guys, what they're doing in a sense is that they're allowing themselves, they set variables and then they allow themselves to backtrack a little bit. Okay, and as you're backtracking, you're essentially giving yourself a perturbation. Now, if over the distance in which they're backtracking, you're not able to jump from one set of solutions to another, you can be stuck at a local minimum over here in your GSAT problem and never get to the true minimum. And so this is why these notions are really important notions. It tells you whether the kinds of algorithms that people use to try to solve these satisfiability problems in real world applications, like how you build computer chips and stuff like that, have a chance of working in certain regimes.
Yes, that's right. And yes, basically one of the motivations for this reconstruction and clustering definitions is that it seems like many local algorithms, they work only until this point, reconstruction, clustering. And actually it seems like in many of these CSP problems, reconstruction and clustering are coinciding. Like the location is roughly the same. But just from the definition, you cannot, okay, they are totally different. Okay, you can have reconstruction and clustering and vice versa. But in CSPs, it looks like it coincides. Some physicists, they have some intuition of why, but okay, that is just some heuristic. Okay, so now I will introduce a series of definitions over Boolean functions because here the definitions will be more important than the results. Okay, like at the end we will say, okay, this result is because of that definition, and not vice versa. So, okay, one initial definition is kind of a trivialization, but it's important to mention is that okay, a pool of clauses of Boolean function is called permutation symmetric if whenever you have a Boolean function, you also have the Boolean function that with the variables permuted inside the pool of clauses or pool of Boolean functions with the same probability. Remember that we have fixed a probability distribution over the pool of Boolean functions. And actually, this is not that I call it a trivial property because okay, you can always basically whenever you have a pool of Boolean function, you can always symmetrize the pool of clauses so that symmetrization holds, and the resulting CSPs from the original pool of clauses is equal to the resulting CSP from the new symmetrized.
So you just add in all the other
yes,
clauses with the right
exactly, with the right
probabilities.
product, and that's it. Okay, so we can assume that. Second condition, okay, this is a restricted condition. A pool of clauses is going to be balanced if all the clauses are, and there is a typo here, should be a minus here, if all the clauses are even. That is, phi of minus x is equal to phi of minus x is equal to phi of x. Okay, so this guarantees that the space of satisfying assignments is going to be also symmetric. If x is
so you can always symmetrize is because your distribution over the hypergraphs is anyhow symmetric, right?
yes, because the variables are IID choosing.
Right.
Yes, that's right. Okay, so this is a restrictive condition because this rules out, for example, k-SAT. That is an interesting CSP, and many other interesting CSP problems. Okay, and we will restrict from now on over balanced pool of clauses. Another condition that we can impose over
What is a well-known example that does satisfy the balance condition?
for example, not all equal SAT or hypergraph to coloring. Yeah. Another condition that we can impose over the pool of clauses is called feasibility. That is basically whenever you fix k minus 1 variables of the Boolean function, okay, inside the Boolean function, then you can choose the other variable to be either 1 or minus 1 so that you obtain a satisfying assignment. So basically this condition what implies is that you can do pure literal elimination, and it will work the same way as with k-SAT.
And k would be related to like the k of not all equal SAT.
Exactly.
Yeah.
So the arity here is fixed k. Yeah. Okay, this is a restrictive condition, but it's just a starting point from the results. This can be okay. We can weaker this condition later on. Okay, some definitions. Okay, the norm of a Boolean function is just the proportion of satisfying assignment. Okay. So feasibility will imply that that's going to be greater or equal than 1/2, basically. There is another norm theta. Basically, now we have a Boolean function in the pool of clauses, okay, or any Boolean function, and now every variable inside is going to be 1 or minus 1 with probability 1 plus theta over 2, 1 minus theta over 2. That is expected value theta. And this is going to be the expected number of satisfying assignment when we choose every spin inside to be 1 or minus 1 with these probabilities. Okay. And now another definition is the influence of the ith variable of a Boolean function is just the average change when the ith coordinates flips from 1 to minus 1. Okay, basically this. And there is a for here because the original definition of influence is just the expected value of the variance of the when you respect to the ith variable and then respect to the other variables. Okay. Another definition is the derivative of a Boolean function that is not going to be anymore a Boolean function because it can take the values -1, 0, or 1. It's just the difference, okay, half the difference when you swap from -1 to 1, that variable. Okay, those were just a bunch of definitions, but of definitions here it comes another possible restriction you can impose over the pool of clauses that is called polarization. Polarization means that whenever you have a clause in the pool of clauses, or a Boolean function in the pool of clauses, the Boolean function that first negates some of the variables and then apply the Boolean function is also in the pool of variables. This is S is just a way to put negation.
What satisfies that?
For example, not all equals sat
Not all
or k-sat, but we rule it
Yeah,
out
but you've
now.
already ruled that out. Okay.
Okay, but okay, this condition won't be imposed. I just will mention that condition at the end. Okay, but for now we just impose balance, and this form.
So people don't know what not all equals sat is. You might just mention.
Okay, not all equal sat is gonna be imagine a disjunction is gonna be satisfied if always unless everyone is 1 or everyone is -1. So that's gonna be a new disjunction. Replace in case sat the
You can have bars.
yes, exactly. And you can have bars. Yes, that's right. Okay, but the condition that we will impose is this, that basically when you have a Boolean function, suppose k is big, most of the satisfying assignments for this Boolean function have roughly the same number of 1s and -1s. Or those are the most frequent. Okay, if you have just a trivial Boolean function that is going to hold, like a Boolean function that is always 1, that is going to hold just because of concentration of the binomial. Okay, but there are two forms in which we can define this dominance of balance assignments. Basically, okay, the log of this is the norm when this is basically this is concentrated around the assignments which have roughly theta 1 plus theta over 2 1s and 1 minus theta over 2 minus 1s, while this is just this norm expectation. Okay, this norm is going to be concentrated over symmetric. Okay, satisfying assignments with the same number of 1s and minus 1s. So this is a way to express that dominance of balance assignments. Okay, this is an entropy form and an energy form. You can express this in many other ways, but okay, we just choose it these two ways. These will be the appropriate ways that will help us. So the specifications we need, okay, we always need here is balance, dominance of balance assignments, at least in the entropy form or in the energy form for only the clustering results, and feasibility. This is just a starting point, but it's not crucial. So some examples of clauses that will fit here, I'll restrict only to 3 examples because the other examples don't have name. Okay, you have many kind of Boolean functions here, but okay, these are the ones with names. Basically, 2 coloring hypergraph, not all equal sat, and source sat. Okay, this is just the summation mode 2.
Does that that doesn't satisfy that condition that you can like negate some of the put s's in there?
Yes, doesn't satisfy that, but we don't require that. Yeah, only these are the main conditions we require. Just balance, dominance of balance assignments, and feasibility, or some weaker form of feasibility. Okay, I just mentioned that condition polarization because at the end we'll simplify some results. Okay, so some related results before I put the location of these properties. Okay, for k-sat, clustering, remember alpha is the ratio of closest to variables. For k-sat, clustering is happening after this location. Satisfiability, k is the arity, the number of variables inside every clause. satisfiability happens until here. And the best polynomial algorithm, okay, it's a very recent algorithm, happens until here too.
What do you mean by the best polynomial algorithm?
None. Yeah.
Oh, okay.
Yeah. None until. For k-coloring, okay, this is not a...
There's no little O of 1 or so. This is really exactly the same threshold.
No.
Here I'm
there.
off
The
by...
best polynomial algorithm? What is it?
Yes.
you mean in this...
So that it's not O of or this plus little O of 1 or something like
yes, this is actually plus... There are second order terms. Basically...
for large K.
Yes. You
And
can,
so the two thresholds are not exactly the same.
yes,
They only
that's right.
become
Yes,
for large K the
yes,
same.
yes, that's right.
Mhm.
Till what alpha does this random assignment work?
Say that again?
Till what alpha will, like, if I just do a random assignment?
Alpha was the ratio of closest to variables.
Yeah.
Basically, we...
Until when do random assignments satisfy it?
Okay. Until when... you mean for KSAT or for...
KSAT, yeah. Just
Okay,
I just want
until-
to compare what I just...
Until here. Your question is until when a random assignment is gonna satisfy.
Yes.
Okay, that's another question. That's a different question because now you take a random assignment and you want the space of satisfying assignment to be small.
Yeah.
Okay, that's another question. That can happen before than this. That can happen
Yeah,
before than that.
small to
Yeah.
know what it is.
Yeah, but that's an interesting question. Actually, for k-coloring, recently we're kind of studying that question, and it happens roughly at this point, also at the satisfiability point. Also, okay, the point in which actually solutions vanish respect to the uniformation of all coloring.
So you're saying that the Bose polynomial time algorithm is not better than random
For
coloring and large K?
for coloring large K. No, is his question that another question is the following. You just take
There's
okay.
a factor of 2.
Yes.
There's a factor of 2.
No, he says...
He set up to 2 k log k, and the best polynomial algorithm is k log k.
But he said they
No.
recently have a random... they proved
Yes.
that random coloring works for alpha smaller k log k.
No, I was wrong. Yes, what we saw that for trees. We saw that for trees, not for graphs. Yes.
I see.
Yes.
For what? Oh, for
trees.
trees. Oh.
Now for trees, if you take a random coloring over all the possible colorings, after this point, that won't work. Okay. For trees, for graphs, here. Otherwise, you can do the trivial algebra. Yes. Okay. And here's the motivation. Basically, okay, one small motivation is that when you have non-reconstructibility, that is non-insistence of long-range correlation in the sense we define, is necessary for fast mixing in this sense. But maybe you still have polynomial fast mixing for Glover dynamics. I mean, but maybe you have anyway after reconstructibility you have maybe some polynomial algorithm anyway. Okay. And also non-reconstructibility is expected to be sufficient for a variety of samples, and there is some intuition for this, but okay, it's out to make this rigorous. So the results are the following: are basically in the same with the same spirit of the previous results by Cleopas and all these persons. Basically, that for example, satisfiability will exhibit a sharp threshold, even counting, for example, the property you have at least b to the n, b is a fixed number, b to the n satisfying assignment. That property has a sharp threshold. Okay, so you can locate these thresholds using second moment methods, even if they are not. Yes. Yes. Sensitivity. Yes. And also, to have a sharp threshold basically implies also that if you use cut certain, you have a random CSP and you choose some, you're an opponent and you choose some small clauses, you modify some small clauses to make the CSP different, then that will make it different. Okay, that's conclusion of sharp thresholds. You also have transfer terms. I'll mention this in a moment. And we can locate where is satisfiability, reconstruction, and clustering. But the thing about these locations is that they are the alphas where these locations are just nonlinear solution to nonlinear equations like fixed points of certain iterations and so on. So we want the results to be when the arity is big, like like these results. Okay, when the arity is big. When the arity is small, when k is small, these results can be difficult. Okay, because when k is big, you can have some asymptotics. So the locations are the following. Okay, first of all, a random CSP is going to be characterized for this. There is something trimmed here for these three quantities. Okay, imagine there is something here. 1 over omega k is going to be used. This is the influence of the first variable. We can take any variable with feasibility imbalance. Any variable will have the same influence, and this is the expectation of this ratio of influence over all the pool of clauses. Okay, this is a quantity kind of the same with kind of the same spirit. Okay, and there is another quantity here. Okay, it was trim. I didn't notice that it used the same expectation, but the same ratio, but you put expectation here and here instead of outside. So the threshold for satisfiability will be between these two values. Okay. Basically this omega k and this omega k hat. Okay. Sorry about that. There is a log 2 here also. Okay, log 2, log 2. The threshold for reconstruction is going to be located here. Depends only on this quantity. Okay. It depends only on the influence of any variable. And the threshold for reconstruction is going to be located here. This omega k, okay, this curve hat is the other quantity that was trimmed here that is basically the same as this, but with the expectation inside. So if basically, if for example you have all the Boolean functions in the pool of clauses have the same influence, then these two coincide. Okay, there is a second order term also. Okay, but the fact that this coincide is just coincidence. Okay. So in the samples I just mentioned, this is what is going on. Okay, threshold for reconstruction and clustering for two coloring hypergraphs located here with alpha above alpha equal to this. For satisfiability is here. Coincides with the known threshold for satisfiability. This is well known. For not or equal sat, same thing. Okay, not or equal sat is actually the polarization of this. Okay, so a good question is polarization actually influence? Maybe not. And for source sat, the reconstruction and clustering threshold is here. Source sat is something easy to solve. Maybe not local, but it's just Gaussian algorithm. But anyway, reconstruction and clustering are happening in early steps, while satisfiability actually happens here. It's just that these bounds I showed before, these bounds are not tight enough. They are tight when the influence is large. Okay. Okay. How much time do I have? Or
I think maybe 5 more minutes or something. So not maybe 10 minutes. Okay, 10 minutes. But
okay.
Well, he's going to be talking to individual people as well. So maybe just give some very high-level idea of the proofs, but not the details. And then when you talk to individual people, you can go into them a little more.
Okay. So, for example, okay, satisfiability is for these problems I mentioned is it's a well-known thing. Satisfiability is a problem that, for particular problems, is somehow easy to study in certain cases, and in order to obtain upper bounds, usually use, okay, the first tool is use a first moment method. So when the expectation of the number of satisfying assignments goes to 0, okay, that's an upper bound for satisfiability. And basically the large deviation for this expected number of satisfying assignments is going to be given by this exponent. By this exponent always, that you have balance, okay? So that's why we require that condition on balance, or on that domination of balance satisfying assignments, okay, in this form. Okay, we want the alpha says that this is exactly here at 0, and okay, we just replace this by 0 because that is going to be the maximum. Okay, that's why that condition appears. Okay, it's natural condition. So for a lower bound in satisfiability, okay, the first thing you can try is a second moment method or a weighted second moment method. In a second moment method, the quantity involved in when you do the calculation is the number of, or the weight of the pairs of solution with overlap theta. The overlap is just the overlap is defined just as the number of positions in which two pairs of solutions are equal minus the number of solutions in which number of positions in which they are different. Okay, just the internal product, x times y divided by n. That's the overlap. That's the quantity you count here, and that's given by this expression. Okay, and now analytical conditions are going to be required. This here, t theta, is the Bonamy-Wegner operator. That is basically the Bonamy-Wegner operator evaluated at close at x is going to be just randomize this x multiplying by this s that are 1 or minus 1 with expected value theta. Okay, basically you add noise to this x and now evaluate phi. Okay, that's also called the noise operator because of that. So we need to impose, once again, we need this to maximize when theta is equal to 0 to obtain the same results as with k-sat or k-coloring. So to guarantee that, this is the condition. This is the condition we need. We need that, I'll put this in another form in the following slide, but this is the derivative. That is the one that gets track of the influence of every variable, but in a more specific way before taking norm. And basically we want, I'll put that. What's happening? Oh, maybe there is a he upload. Okay, basically, this is supposed to be a different slide. I don't know what happened with it. But basically, this will mean another equivalent formulation for this is just theta, t theta here, maybe a different constant, but same form, but t theta here. Okay, this operator is self-adjoint. Okay, you can put it here. The square root is just t of theta to the 1/2. Okay, but anyway, another way to express this condition is that t theta phi derivative is less or equal in norm, is less or equal than this quantity times, okay, norm of the derivative. Basically, this means this is equivalent to a kind of tightness of the hypercontractivity inequality over the derivatives of the pool of clauses. This is the condition necessary, or this condition will be sufficient, like to have the concentration of this exponent around overlap 0. Okay, sorry about that. That the slide is missing. Okay. So yes, there's some slide missing here. I don't know. Okay, so that is what is going on with satisfiability. So two analytical conditions come into play. Okay, but this second one is the more important. Another equivalent formulation of this is that the Fourier coefficients, okay, every Boolean function can be expressed as a polynomial in a unique way. So this condition will imply that the low coefficients, okay, the coefficients of the low terms for the derivative or for the original clause, not counting the constant term, are going to be dominated exponentially by the whole by the whole sum of coefficients. Basically, they don't count too much with the norm.
The influence, or I mean,
Yes.
yeah.
Yes, about influence, but not of one variable, but of just a small number of variables. Okay. Basically, the influence of a small random of variables, where the small is not clearly defined, okay, is defined here implicitly, is small. That is basically this condition. Sorry about the mixing slide when I put this equivalent condition. Okay, what happened with reconstruction? Okay, the thing about reconstruction here is that in this regime, ratio of closest to variable equal to a constant alpha. What is going on? Okay, what is going on is that when you look at the hypergraph locally, it's going to be a tree. Okay, you just pick a random vertex with high probability. You look locally, okay, say range L, or then it's going to be a tree. So there should be a relation between tree reconstruction and actual reconstruction. Okay, there is a relation, but what's the missing point? The missing point is that, okay, reconstruction over a tree is something easy because, okay, how do you construct the space of satisfying an assignment over a tree? You just broadcast all the possibilities over the tree. There is no restriction. But over the graph, okay, you start broadcasting, but at some point now you are not in a tree anymore, so you have restrictions. So actually the marginal faraway points in the tree and in the graph, they don't coincide. So in the definition of reconstruction, okay, there are different definitions, but there is a, okay, Montanari inversion field came with these two conditions that guarantee that actually the marginals are going to be close of faraway variables. These are the conditions. Basically, you need that a random satisfying assignment of the CSP to be roughly balanced in the sense that you have almost the same number of ones and minus ones. And that is guaranteed because of the dominance of balance assignment of every Boolean function. And also, you require that any two pairs of independent random assignments have approximately zero overlap, meaning that the positions in which they coincide is almost the same as the positions in which, almost the same number as the positions in which they don't coincide. So you take two independent random satisfying assignments. You look at in which positions they coincide. You look at which position they don't coincide. So they have to be almost the same. They have to be almost the same. That is the overlap.
It's not going to always happen.
No. So this is going to happen until a certain point.
Yeah.
So you have to locate that point. Okay. And under these two conditions, okay, so local reconstruction, basically, when you look locally at the graph or at the hypergraph, coincides with global reconstruction. The marginal far away vertices are going to be almost the same as when you broadcast. And finally, some remarks about clustering. That, okay, if you have polarization, you don't need any more. But if you don't have polarization, you need these technical conditions regarding Fourier expansion or regarding Bonamy-Wegner operator.
Uri Feiga do some work on this at some point?
Say it again?
Did Uri Feiga and someone who was a student, and I now forget his name, do some work on satisfiability with these planted assignments and what it means in terms of the structure of...
Yes. Actually, the first thing here is that one of the results here is that a planted model, okay, you have a transfer theorem, basically for this CSP until a certain point.
Right.
A transfer theorem means that the planted, if you have something that is satisfied in the planted model with a probability 1 minus e to the minus n, certain constant, then it's going to be satisfied in the original model with probability 1 minus little log 1. Here it holds. The planted model is going to be, okay, there is a transfer theorem. And using these transfer theorems is the usual way to prove clustering. So for clustering, unless you have polarization, you need this condition of Bonamy-Wegner operator to be to change. Okay, you need that condition to be of this form. So, for example, for two hypergraph colorings, you have to check this condition, for example, and that holds here. But notice that this technical condition is only for the result when the arity goes to infinity, when k is large, to hold. Okay, to obtain the corresponding asymptotics. Okay, so I think I'll stop here. Sorry for some typos and a missing slide.
Any other questions and comments from someone other than me or Crystal? Or Adam. Well, Adam can ask half a question. Ask how or why. Not complete.
Why?
So, any other questions? Okay, well, you're going to be meeting with a lot of us during the day, so we can ask you more detailed questions. Okay, thank you.